Thank you everyone for joining me for today's webinar series, Did You Know? My name is Eric Wright, and today I'll be talking to you about perceptually uniform color gradients. Before we can start talking about perceptually uniform color gradients, we have to understand what that means. To get started, we're going to have a little demonstration. On your screen here, you see the word Petrosys. It's written in black font on a white background. This contrast makes it easier for you to see the words very quickly at a glance, and there's no obscurity. It's very easy and clear to see. If I were to change the background to green and the font to yellow, well, it becomes slightly harder to read because the contrast between green and yellow is a little bit less than it is between black and white. As an additional fun puzzle, I've also included this yellow dot here at the bottom right of the screen. You may have noticed that dot instantly, but I'm putting it here to make you think about how we use color to represent visual data. Some of you may have not seen the dot immediately. It's important to use an appropriate color scheme to visualize data properly. And a lot of times you'll see people use a rainbow color gradient, and there's better ways to visualize your data. The rainbow color gradient is prevalent whether we're working with structure maps or temperature maps or gravity and magnetic data. But there's different ways to visualize things than just simply the rainbow gradient. And that's what we're talking about today. So defining perceptual uniform, this is kind of tricky because color is something that's personal to each of us. For example, what I see as blue may be what you see as orange or yellow, perhaps. So how do we define perceptually uniform? The best definition I could find online, or at least one that represents the the statement well, is by Fabio Crameri, who's done a lot of work in this area. And the definition states that a perceptually uniform color map weights the same data variation equally across all the data space. So how do we give weight to color? Well, in 1931, the International Commission for illumination, came out with this work. They collated some previous experiments discussed regarding the RGB color space, and they came out with this chromaticity diagram. This diagram and this work that they did laid the foundation for all kinds of color advancements, such as movies and TV and computer screens and dyes and inks. And even though we've revised this diagram many times since, it's still thought of as it still provides a good basis for the understanding of what perceptual uniform means. So what you see here, it's a way to relate wavelengths of visible light to what humans see as visible color. On this black outline you see here, you'll see numbers, and each one of those numbers is a wavelength of perceived light. I'd like you to note that between 500 nanometers and 560 nanometers of perceived light, you'll notice that there's a lot of green. There's very little perceptual change in the shade of green that you are viewing. Whereas if you take that same band, that same length of light, say, for example, between 560 and 620 nanometers, you'll see a lot more perceptual contrast. In other words, the color goes from green to yellow to orange to red. Or if you look from the lower end of the spectrum, you'll see the same, a similar, more drastic change, say, for example, from blue to cyan to turquoise to green again. The green itself is kind of a dead zone, and it leads to some problems when we're creating perceptually uniform color gradients. I suppose the main point to get across here is that visible light is not perceptually uniform. Wavelengths of light actually change not in accordance with the way we perceive color to change. And to understand that even better, what I have here is a standard color bar. This is a rainbow color bar. And the way most rainbow color bars are constructed is that the computer programmer or the computer program itself will actually assign a bunch of control points or anchor points along the color bar and then set the computer to run a linear interpolation between the different anchor points you have. And it's not necessarily a linear interpolation, but in this example, I'm using a linear interpolation. It's some kind of interpolation. Um, if I draw black lines here between my anchor points, it makes it a little easier to understand. The difference in width between these anchor points is not standard. In other words, the length between the two purple anchor points is mathematically uh, different than, say, the 2 points between, say, cyan and green, which is much longer. Uh, this rainbow color bar isn't perceptually or mathematically uniform. Whereas if we use something like the Batlow perceptually uniform color bar, which is provided in the Petrosys software package, you can see that there's a lot more care that has gone into selecting the different hues along this color bar to make it to where that each one of these hues is perceptually uniform. And if I were to draw a black line at each of these anchor points, it would cover the entire color bar. So why do people use rainbow gradients at all? I can see a couple of reasons why people might use rainbow gradients. One, they are very handy when you're working with a more discrete color bar, such as what you're viewing on the left-hand side here. If you're working with a discrete color bar with only, say, less than 10 points, it might make sense to use a rainbow color bar because the different colors in the rainbow color bar actually provide a lot of points of different contrasts. Our eyes can pick out, say, orange, the difference between orange and yellow fairly easily, or yellow and green, or green and blue. Whereas something more like a perceptually uniform color bar or a more continuous color bar, such as the one on the right, sorry, a perceptually uniform color bar may be a little harder to have those points of contrast. Perceptually uniform color bars aren't going to have that many different points of contrast. Secondly, rainbows are familiar and rainbows are attractive. If you turn on the news and you look at the weather report, you'll see rainbow color bars probably representing the temperature of your area or the weather in your local region. And they look pretty. Humans like seeing all the pretty colors. We like seeing red and yellow and blue. Another reason why you might see people use rainbow color bars is that they may want to bias a part of what they're representing. There are certain colors on the rainbow color scheme that actually draw our attention very quickly. Red is a very well-known example. If you're looking at a red part of a structural map, your eye is going to be drawn to it fairly rapidly. So why should you consider not using rainbow? And that's what I'm here to talk to you about. The rainbow color bar is not the ideal color bar that you should use. The first reason why you shouldn't use a rainbow color bar is that the non-incremental contrast in this rainbow color bar actually makes the values, the underlying values that these colors represent, fairly hard to determine. In other words, if I were to give you just 6 squares of random colors and asked you to order them from least to greatest, well, you would probably need a color bar to do so. Whereas if they were all different shades of blue, you could probably figure out, and by using that incremental contrast, that it might go from dark to light blue or from light blue to dark blue. You'd be able to order them fairly intuitively. But the rainbow color bar does not provide that incremental contrast. Instead, it uses hue segmentation. So you'd have to look at it and determine whether or not green is worth more than orange, or is orange worth more than red? And that's very difficult to do intuitively. Another reason why you might not want to consider using a rainbow gradient is that the colors themselves that are on the rainbow gradient aren't equal in luminance. And luminance, you may think of it as brightness, for example. In the middle of the color bar, most rainbow color bars will have cyan or light green or yellow, and these colors tend to be brighter than the colors at the outliers, such as blue, red, or purple. And in fact, these luminant colors can often attract your eyes to false features, which I'll show you in a bit when you're working with geologic maps, such as structure maps or amplitude maps. The brightness kind of draws our eyes to, or washes out features when those colors are present in the color bar. And to get an idea of the luminance of a color gradient, you can always change it to grayscale. And what I've done is I've simply taken the rainbow color gradient above And I've used PowerPoint, which allows me to display it in grayscale. And you can see in the middle of the color bar in grayscale, it actually looks more white than at the ends. And while we're speaking about grayscale, an ideal color bar should also be friendly to the colorblind. About 300 million people in the world have some form of color blindness. That's 1 in 12 men or 1 in 200 women. A scientifically designed color bar should be take that into account. We want this color bar to be as representative and as communicative to as many people as possible. We don't want to leave any of our colleagues out just because of color blindness, for example. What you're seeing here is a chart of different perceptually uniform color bars and how they look to the color vision deficient or in grayscale. And compares that to the rainbow color bar at the bottom. You can see that the perceptually uniform color bars all have some form of incremental contrast for the color vision deficient, as well as the colorblind, or as well as a grayscale. Whereas the rainbow color bar, that's not necessarily true. A geologist should probably not consider using rainbow because, again, the low perceptual contrast can often wash out your geologic features. Colors with bright luminance, such as cyan, yellow, and green, can often attract your eye to features that are not that are present when they may not be. What you're seeing here is just a little snippet of an amplitude map that I have. On the left, you have it being displayed in a rainbow gradient, and on the right, you have it being displayed in a Batwow perceptually uniform gradient. You can see how the green washes out a lot of the linear features as well as a lot of the highs that are present inside that amplitude map. On the right, the Batwow, it seems a lot more clear, and my eye can detect the linear features inside this amplitude map a little bit better, and it can also it's not drawn or distracted to certain high areas such as might be present in the rainbow map because of the color that the rainbow map uses. So what color bars should you be using? And these are Fabio Crameri examples that are present in Petrosys. We have a lot more than 3 color bars, which I'll show you in a second. But some basic recommendations that I might offer you is there's the Batlow color bar, which is a good default color bar that mimics the standard rainbow bar that people like to use. There's also the Davos color bar, which may be good for bathymetry. And there's the Lajala bar, which is good for temperature maps. But you don't have to stick to these recommendations. I encourage you to explore and to use different perceptual uniform color bars to find one that might suit your purpose. And now just for a quick look inside the software to see how these color bars might affect our visual perception. Let me go bring over my Petrosys map. What you're seeing here is a map of the Gippsland Basin inside of my Petrosys mapping window. You can see it's being displayed in a rainbow color bar. The high points of this basin are represented in red and yellow, and you also see this band of green, cyan, and yellow kind of around it, with purple representing the lows. If I turn on a perceptually equal color bar, or perceptually equal gradient for the same basin, you can see now that certain features aren't as washed out in the gray and cyan area. For example, this sinusoid feature here becomes a lot more present, and it's a lot more visually attractive for me to see. It's easier for me to see anyway. And I think you might find the same result. To turn on a perceptually equal color gradient, what you'll do is simply double click on the surface inside of our display list here, and then that'll bring up our display properties menu. Let me make this a little bit bigger. And the color gradient is going to be listed here in this little color gradient button. If I select this color gradient button, and if I sort this by name, inside of Petrosys, the perceptually equal color gradients are all going to be labeled Fabio Crameri. We have about maybe 20 of them here, and there's different colors. And again, this is just displaying the Batlow, which is the one I use. It's a good all-around color bar, but you can see that we have several others also listed in the program. One of the features that we also have for color bars is this equalization bar. If I click on this equalization bar, what this does is it distributes the color gradient across your entire data space. So for example, it makes each color represented equally in the data. So for example, if I go back to this rainbow color bar, this is the non-equalized rainbow gradient being displayed. If I use an equalized color bar, you can see how it changes the rainbow gradient. It makes the reds more prevalent as well as the purples on the outside. And if I turn on the color bars so that the actual color bars so that you can see them on the right-hand side, the left-hand side is the non-equalized color gradient, and the right-hand color bar is the equalized gradient, and you can see how it's distributed the colors across my data set. It's made the purples more prevalent, the reds more prevalent. It's ensured that this data has these colors are now equally represented in my data. If I do the same thing for the batlow, just to compare, see if I turn this on, you can see how an equalized color bar might affect the batlow, and it's made the pinks a little bit more prevalent here, and as well as made the darks on the outside more prevalent there. Turn off this color bar. There we go. So you can see that you can compare it. See, there's not as much difference when you're using a perceptually uniform color bar with the equalization feature because it's already designed in part to be perceptually uniform. One of the other things you might notice, I double click on this grid here in Petrosys, is that we have different ways to display your color gradient across your data space. If you click on this drop-down box here, we have 3 different ways we can apply your color gradient to your data. The first option, the dynamic data option, simply takes your entire data space and applies the color bar to that data space, the entire data space. So if your data space is 1 to 100, your color bar takes it as being 1 to 100 and applies it as needed, even if the color bar itself extends past 1 or 100. Dynamic data clip to map sheet, which I'll show in a second, actually takes not the entirety of your data set, but it takes or ingests the data that is currently present on your map extent and then applies the color bar to that as appropriate. So for example, if my surface was from 1 to 100 meter subsurface, but on my screen I was only showing 25 to 50 meter subsurface, the color bar would be applied to 25 to 50 meter subsurface, and applied to that only. And it would stretch itself out, so to speak. The fixed custom range allows you to apply a specific color range to your color gradient. So if you only want to display your color gradient from a certain range of data, you can use these input options there as well. If I were to zoom in now or change my extent to this sinusoidal feature here, you can see, let me see if I can compare. I have another screen here, which will allow you to compare what a color gradient might look like. Let me see if I select this sinusoidal feature here by changing my extent. Give it a second to draw the location map here. Okay. Excuse me. All right. So you can see how the color bar is applied. On the top color bar here, you can see that this is a color bar that's being applied to the entirety of the data set, and it has not modified the color bar in any way. But by using the dynamic color bar, the one that's clipped to my map sheet, you can see the difference here. The black color is more prevalent, and it's being applied as if the lows of my data are now at the border of my screen, rather than in this version, the lows of my data having to be off screen. So I wanted to show you that. Hopefully that helps you out a little bit. And the next thing I want to show you is if you wanted to create a color bar in Petrosys, you can do that by going to Edit and Gradient, and that will bring up our gradient editor here. If you want to create a color bar, you can see here that our color bar is created by first assigning a bunch of control points, which is indicated by these arrows, and then by running an interpolation algorithm between these control points. If you were to load a perceptually equal color gradient, you might get something that looks like this, which again has several anchor points. and has been carefully designed and picked so that each one of these hues is perceptually uniform. Initially, when I first started doing this webinar, I wasn't a believer necessarily in perceptually equal color gradients, but as I got to use them more in my work and my exploration work and my mapping, I'm a believer now. I encourage you to consider applying some of these perceptually uniform color gradients to your own data sets and see how they can improve that. I'd like to be thankful and acknowledge Fabio Crameri and some of the work that he's done for the perceptually uniform color space, as well as several other websites that I used in the creation of this webinar. The research itself is quite expensive and into color, and it's very interesting. So thank you all for joining me today. And if you have any questions, please feel free to email me at eric.wright@petrosys-usa.com or contact us at info@petrosys.com.au or visit our website, www.petrosys.com.au. Thank you very much, everyone.